Okay, if anybody's having clicker problems, come see me before class starts. We have 4 minutes. If you're having clicker problems, come get some help.
I'm not necessarily having them, but this was the day that I was not here. So I was in class on Zoom, but I wasn't in person and I hadn't set this up yet.
Okay, so send me that in an email and I'll fix it for you.
Okay.
Okay. And we rocked and rolled last class, so we should be doing good today. Do I have everything? Let's see. Okay. Oh, I opened that with the wrong thing. Okay. I think I am good now. Can you hide this completely? Let's see. Oh, hide video panel. Yay. One last thing on the screen. And then what? No. That's okay. Okay, so I'm gonna start this just so y'all can do this whenever you get a chance. How y'all doing? Okay, making it? Happy Thursday? Friday Eve. Friday Eve. Not Thursday, Friday Eve. All right. Give everybody another minute. All right, so I'll go ahead and get started. There are a few things I want to go over. Right now, everybody should be doing their clicker attendance, so I'll leave that run for just a few minutes. And I put in an announcement yesterday. If you did not get an email that you got, that I posted an announcement at the end of class, come up and let me help you change your settings so that you make sure you get my announcements. This is something that should automatically send you an email, something saying I posted. So a couple of people asked me in general, what's the best way to study? And they wanted some extra help on a few things. So I'm gonna go over this real quick. When you're preparing for this class, what I suggest you do is break it up into bite-sized pieces. And by bite-sized pieces, I mean by section pieces. So take one section at a time, read the section first. Then go and watch the video that's specific to that section. Then you'll come to class, you know, and you do that for however many sections we have before class. Come to class, we do all the problems from those sections. Now that you have all the practice, go and do the homework on the Mastering Chemistry side, right? If you have problems, then that's the time to say, oh, Dr. B, I need some help. I was doing these problems on Mastering Chemistry and like, I couldn't do it on my own. You know, when we were together, it was working, but when I'm on my own, something's not clicking, and I'll help you. You know, we can Zoom, we can whatever, and I will help you. If you want to take a picture of your work and you want me to, you know, annotate your work, okay, you should have put this conversion factor there, whatever it is, I will help you, okay? And then you should do that for all the sections, then you should be ready for the exam, right? So go back, read over your notes, read over your book, things like that, but use the book. I'm going straight through the book. Please use it. It's a really good resource. If you're online, there are videos embedded in the ebook that you can watch that are really helpful. And a few people asked, okay, I'm having trouble balancing equations. So I went online and I got a couple of videos for balancing chemical equations. So it gives you examples and it works you through how to do it. So I put a couple of those. Then some people asked for extra help with dimensional analysis. So I put a video for converting with dimensional analysis, and then what we specifically did in class and what you will see on the exam is using conversion factors to do drug dosage calculations, right? That was the drip rate and all that kind of stuff. So I found a Khan Academy video where they do a few examples. So is it required that you go and watch these? No, but it would help. You know, if you're struggling, that would be a good place to go. And if you come up with a topic, Dr. B, I'd like some extra videos on XYZ, I'm happy to go find some and post some. Just let me know, okay? All right, good. Okay, and I think that, oh, and on your iClicker, my other announcement, I always had this little sheet of paper, things to cover with y'all. On the iClicker, for your student ID, you should have one of two things in your student ID. You can either have your N number or your student email address. So I make sure that it correlates with my grade book. So when I import to Moodle, your grades transfer over. So check your student ID on your iClicker should either be your N number or your Nichols email address. Good? All right. So you should have watched all the way up through section 5 today, right? Chapter 2, section 5. All right, we're gonna rock and roll, but I'm gonna give you a couple of quick clicker questions first to make sure you actually watched. Sometimes I will do this. Sometimes it's a wrap up, sometimes it's a did you watch the lecture questions. Okay, so I'm gonna stop the attendance poll. Did everybody get to respond to attendance? If you have not done so, please do so right now. Okay, I'll call that one. All right, so here we go. How many electrons are present in a neutral atom of potassium? You might want to use one of these. You could bring one to class every day. It's like your best friend, periodically. It doesn't carry coronavirus either, so you can get real close. And I'll give y'all 1 minute to respond. And that's supposed to be 1 minute, but I know that's not everybody responded. Please respond. 10 seconds. I only have 48. I only have 48. Where can I get a periodic table carried around? You could take a picture of the one in your textbook. You could print out one from the internet. Doesn't matter. They're all the same. Okay, 48. All right, so what did we say? 19 is correct. 19. How did you figure that out?
The number of protons.
It was the number of protons. So if you look at the periodic table, right, and we find potassium, potassium is number 19. And if we are a neutral atom, neutral means what? No charge. That's what neutral means, no charge. So that means that the number of positive charges must equal the number of negative charges. So positive is protons, negative is electrons. So if you have 19 positives, you must have 19 negatives, right? Okay. All right. Atomic number is what? Okay, I'm calling it down. All right, so atomic number is equal to B, right? The number of protons in each atom. So if you have, right, a box from the periodic table, if it's carbon, what number's on top of the C? 6, and that 6 is the atomic number. What is the atomic number? Equal to the number of protons, which is equal to what? In what? Be careful. A neutral atom. So usually if we say atom, we mean neutral. And if it's not neutral, we say ion. So if you see atom, you can basically assume neutral. Oh, I gotta erase. I forget this. Oh, I learned a new trick. Clear ink. Haha. I feel so proud of myself. All right. Here we go. Protons have blank. I'm really calling it at 1 minute. So everybody needs to get their answer in about 1 minute. So what did we say? Protons have a mass of about 1 AMU and a charge of +1. All right. Where is the mass of an atom located? In the nucleus. What particles are in the nucleus? Okay. So now, the next ones, the answer choices do not change. Electrons have what? What do we have, 40, was it 48? Was that our max? No, 49. I'll still give it a minute, but I try to watch that. Okay, so what do we say? So electrons, oh, be careful. Electrons have a negligible mass. So, y'all are gonna see there's one that I just messed up on that. I'm gonna delete that after class, so don't worry about it. But electrons have a negligible mass and a -1 charge. The other thing people said was there's a mass of about 1 AMU and a charge of -1. But what did y'all just tell me? The mass of an atom is where? In the nucleus. Where are the electrons? In the electron cloud. So there's negligible mass in the electron cloud. Okay? Which is why we are all mostly empty space. It's like a really weird concept to think about, but it's true. Okay, so tell me about neutrons. I need like Jeopardy music to play during this. I need to figure out how to download that. I bet that's like copyrighted. 49 is our max today. I'll let it go. Ooh, see, we got 50. All right, so what do we say? Good, good. So we have, neutrons have a mass of about 1 AMU and no charge. Neutrons are neutral, right? But they do have a mass. So that was your quick, did you watch? Did you watch? And we'll have some more iClicker questions next time. But we are going to switch gears and we're going to go to our in-class problems. So pull that up, take that out, whatever it is. You will need a periodic table. You will absolutely need a periodic table. So let's be using it. All right, where are the subatomic particles located in an atom? I thought we did this one on the video, but did I not? Guess not. Okay. Tell me about protons. Nucleus. Tell me about neutrons. Nucleus. How about electrons? Electron cloud. Okay. How does the mass of a proton compare to the mass of a neutron? They're approximately equal. How does the mass of an electron compare to the mass of a proton? It's 1/2000, right? Of a what? Like if I say I have 1 proton, that is equal to 1 AMU. So this is 1/2000th of an AMU, right? And that's an electron. You know our little symbol notations, right? You need to be familiar with that. P plus is a proton, N0, neutron, and E minus, electron. Okay, what units? We just said AMU, but tell me, what does AMU stand for? AMU. Atomic mass unit. Look at that, they named something right for once. Sometimes that gets me in science. They don't name things appropriately. But atomic mass unit, it's measuring the mass of an atom. I like it. Okay. What can be determined from the following? Mass number. So it's our number of protons plus our number of neutrons. How about our atomic number? This is just our number of protons. Now tell me, if I have a periodic table, which number that we just described do I see above the elements? So like the whole number above the element. That's the atomic number. Why is the number on top a whole number and the number on bottom not a whole number?
The bottom number is an average.
Well, it's an average. It's math. It has to do with math. The one on top is a counting. I can look at an atom and I can count the number of protons, right? So that one's always going to be a whole number. So if your atomic number is a whole number, you're just counting, and then you also count your number of neutrons, that means your mass number is always going to be what? It's going to be a whole number, or are we going to have like a big decimal? It's going to be a whole number, right? So our mass number is going to be a whole number, no decimal places, and the atomic number is going to be a whole number, right? Okay, the mass, what's the mass number minus the atomic number? Number of neutrons. That is correct. Okay, so now you're going to need that periodic table from somewhere, doesn't matter where. Provide the name and atomic symbol of the element has the following atomic number. Okay, what do we got? 79. Use your periodic table. What is 79? Gold. And what's my symbol? AU. Okay, 19. What is the symbol? 82. Lead. And lead is weird. It is Pb. Okay, 33. I don't think that's right how to spell arsenic. Symbol? AS. RAR. Well, whatever. I'm not a very good speller. Y'all figure that out very quickly. 11. And sodium is another one of those weird ones. It's Na. So somebody asked me, do I need to memorize the periodic table? No, do not memorize the periodic table. Please don't do that. I am going to suggest that you know the elements that are super important for life. I'm not going to test you on that. I'm not going to say what is the abbreviation for lead. I'm not going to do that. But would it make taking your exam quicker? Absolutely. So I will do one of the two things. I will either give you exactly this periodic table and this table right here that has the element names and their symbols, or I will find a good periodic table that has not only the symbol but also the name. But if you're hunting around on the periodic table for 20 minutes, it's going to be a problem. So I'm not telling you to memorize the table. I'm telling you to get familiar with it and be able to use it efficiently. Does that make sense? Okay. You just don't want to be hunting around during exam time. You know, you want to make good use of your exam time. Okay. This helps. Yeah, good. I'm glad you like that. Okay. What is the mass number for a fluorine atom that contains 10 neutrons? So let's write out what is our abbreviation for fluorine? F, right? And so when we look on the periodic table, if you look at the square, there's an F, and what number is on top of the F? What is it? 9. I thought somebody said 7. 9. Okay, so when we write an element symbol, we're going to take that atomic number and put it at the bottom, right? And then we're going to take the number of neutrons and we're going to add the number of protons to that, and that's our mass number. So our mass number is 19. How can you remember where a mass number goes? Well, the really awesome thing about this is that if you put them in the right places and you subtract mass number minus atomic number, this is atomic number, you should end up with a positive number, right? So your mass number minus your atomic number should tell you your number of neutrons. So always put the bigger number on top. That's the mass number. Okay. All right, let's see. Okay, come down here to 2.12. Determine the number of protons, neutrons, and electrons. So I'm going to do a similar grid. Protons, neutrons, electrons. All right. I like to write the symbols so I get comfortable with that. A helium atom that has a mass number of 14. So helium symbol is He. How many protons? 2, and it has a mass number of 4. Okay, once I collect all that information, it's easier for me to look at that way. So tell me about number of protons. 2, and if it's a neutral atom, our protons must equal to our electrons, so we must have 2. Now, in order to find our number of neutrons, we take our mass number minus our atomic number, and we get our number of neutrons. So how many do we have? 2. Okay, let's do the next one. A carbon atom that has a mass number of 14. So you can put your mass number on the top, and if it's carbon, how many protons does it have to have? 6. Okay, so how many protons? 6. How many electrons?
8.
Electrons.
Oh, electrons, 6.
I always do that. I like to do my protons and electrons together. I don't know, just knock them out of the way. But it doesn't matter what order you do it in. Okay, and the neutrons y'all are right is 8. Okay, everybody please make sure you're wearing your mask, that they're covering your mouth and your nose. Okay. All right, let's see. Symbolic notation. Okay, this is what we were just doing, so this is going to be super easy, right? 3 protons and 4 neutrons. What element has 3 protons? Lithium has 3, did I say 4? 3 protons. So what's my mass number going to be? So my mass number is my number of protons, which we said is 3, plus my number of neutrons, which is 4, so it gives me 7. Okay, B. 7 protons. Go look it up. What gives me 7 protons? Nitrogen. And then we get our mass number from adding our protons and our neutrons, and we get 17. Okay. 15 protons. What has 15 protons? Phosphorus. And how many, what's our mass number? 15 plus 16 is 31. Always remember that bigger number goes on the top. All right, and then 46. Ooh, we did a big jump there. What has 46? 46 is, let me make sure I'm right. I don't like to say it wrong. 46 is palladium, Pb. Okay, and how many, what's our mass number? 106, yes. Okay, good. Not too bad, right? Easy peasy. This is what my son says, easy peasy, lemon squeezy. I don't know. He's got some interesting sayings, I'll tell you that. All right, number of protons, neutrons, and electrons. So now we're going the opposite way. We're given our symbol, and we need protons, neutrons, and electrons. So how about that first one, A, number of protons, 1. And so I like to go over and do number of electrons, 1, and then I subtract the 2, and I get 1. I don't know, just it's the way I've always done it. Okay, so aluminum, and how would I say this if I were having a conversation? You know, we met each other on the street, and I wanted to tell you about this really cool element, aluminum, what? How would I tell you that this is the isotope, this is the atom I'm talking about? I would say aluminum 27 is the coolest atom. No, not really, but that's okay. So it would have 13, because that is our atomic number, 13. And what is our number of neutrons? 27 minus 13, which is 14. Okay, sodium 23, protons, electrons, Neutrons. Okay, bromine. We look at our atomic number, 35. That tells us our number of protons, also our number of electrons. Take our mass number minus our atomic number, and we get 44 neutrons. Okay. I need to stop saying okay so often. I know it's a bad habit. So the mass number of the isotope carbon-12 is exactly 12 AMU. The atomic mass for carbon, as seen on the periodic table, is 12.01 AMU. Explain this difference. So let's talk about carbon-12 first. What is carbon-12? How many protons? How many, what's our mass number? 12. Okay, if the only things that really have mass inside of the atom are the protons and the neutrons, then my atomic mass is going to be exactly 12 AMU. Why isn't it 12 AMU on the periodic table? So tell me some other isotopes. So we know we have we have, we know we have carbon-12, but I'll tell you that we have carbon-13, we have carbon-14. What's different about each of those? Our mass number, so right, if I did this, oh, it's getting too close to the top. That's my deal. Carbon-14. Okay, and 6, right? They're all carbon, so they all have 6 protons. But what's different? What's changing that mass number? Number of neutrons. So when we look at that atomic mass on the periodic table, so if you look, right, it's carbon, and we have 6 here, and we have 12.01 here at the bottom. The reason we have 12.01 and not 12 is because we have to look at the mass of carbon-12, we look at the mass of carbon-13, and we look at the mass of carbon-14, and we average them. But it's not a simple average, right? If I did a simple average, what would it be? Somebody help me out. 12 plus 13 plus 14 divided by 3 should give me 13, right? This should be my average. Is that what's on the periodic table? Oh, but I just said it was an average.
It's the weighted average.
It's a weighted average. So why is it different? Well, carbon-12, of all the carbon in the entire planet, about 99% of it is carbon-12. These two make up 1% of the carbon. So when we find that average, we have to calculate that. We have to take that into account mathematically. So we would say 12 times the percent, but we don't do it as a percent, we do it as a decimal. So if I have 99%, what is that as a decimal? We did that last chapter. 0.99, right? So then we would do carbon-13, and we would do its percent. If its percent were, I don't know, 0.5, I know that's not right, but it's like 0.5%. So we're going to move the decimal place 1, 2 times 0.05, right? No, 0.005. Dr. B. Okay, and then the same thing with carbon-14. It's another one that's really, really, really small. Okay, so if you did this and you put that into your calculator, you're going to get, if we put all the numbers right, about 12.01. And my numbers aren't quite exactly right, so it's not going to come out perfectly, but pretty close. Okay, this is why we have 12.01 on the periodic table, because it's a weighted average of all. So the atomic mass of carbon is the weighted. What does the weighted mean? That we took into account what? How much of each? The abundance. the weighted average of all isotopes of carbon. So we know if we change the mass number, we're going to change the mass. But when you look at that atomic mass on the periodic table, it's taking into account not only the changes in mass, but also the abundance, okay? All right, how are atomic mass and mass number similar? How are they different? If I'm going to find my atomic mass, what am I actually going to do? What am I going to measure? The what? The atomic mass? The mass, so mass number, I'm going to count, right? The number of what?
I'm sorry, protons and neutrons.
Neutrons. What am I going to do for atomic mass? Average of what? Right, so I'm going to measure the mass or the weight, right? Measure the mass of, it's still the protons and still the neutrons. So what's similar in my description? How are they similar? I'm looking at protons and neutrons. This is how they're similar. I'm measuring them. But what's different?
In the atomic mass, we take the count of the protons and the weighted mass of the neutrons. The weighted mass of the isotopes.
Right. So when we're doing mass number, all we're doing is counting. But when we're taking our atomic mass, we actually have to determine its actual mass. So it's a different kind of measurement. So it's a different measurement. But it's similar particles. Right? Do we worry about electrons for either of them? No. But they are different because in one we're counting them. Okay, we have 6 protons. And in the other one we're measuring the mass. Right? Okay. So let's talk about some isotopes. I guess I should kind of leave that to where y'all can see it. Is that good? I'll move that over. There are 3 naturally occurring isotopes of magnesium. Magnesium-24, magnesium-25, and magnesium-26. How many neutrons are present in each? Write the complete symbolic notation. Okay, and then we'll determine which one's more abundant. So let's start with our 3 different isotopes. So how would I write them symbolically? Where is this 24, 25, and 26 going to go? Top or bottom? At the top, so I'm going to go 24, 25, 26. Now what goes at the bottom? So if we go to magnesium and we find it on the periodic table, the number at the top is going to be 12. And it's the same because it's all magnesium atoms. Now tell me number of neutrons should be different because these are different isotopes. So do 24 minus 12 for the first one. What do you get? 25 minus 12. 13. And then 26 minus 12. 14. Okay. Now, based on the average atomic mass given on the periodic table. So if I have magnesium, it's 12 up here. Tell me what's the number below magnesium? It's not 12. 12 point what? 24. Uh-huh. Come on. There we go. 24.31. See, y'all should use the chat and I should just be able to write it down, right? Okay. So I just told you that that number is the weighted average of all the different isotopes. So tell me which isotope is more prevalent in nature. So what you do is you look here, and whichever isotope, you're looking for the isotope with an atomic mass with a, not an atomic mass, with a mass number closest to the atomic mass. So it would be magnesium 24, because this atomic mass is close to this. So what that's telling us is we have more magnesium 24, because if you do the weighted average is going to be closer to the mass number of the most prevalent isotope, right? Do you remember in the book that showed you the different carbon isotopes, and they did it like kind of in blocks? And so it was a really tall block for carbon 12, and there was really little for carbon 13 and carbon 14, right? And so what that's telling you is the mass on the periodic table, the atomic mass, is going to be closest to that isotope that's more prevalent. All right. Okay, so we got one more set of isotopes. We have 4 different isotopes of 10. What is my abbreviation for 10? SN is 10. So weird, but it's true. Okay, 118, 119, 120, and 124. I wish there was like a go back erase, but there's not. Okay, so tell me how many protons in each? So if you go look on the periodic table, you should find that there are 50 in each. And so now I just need to go in and find out how many neutrons are in each. And so I just do my subtraction. 118 minus 50 should give me 68. Now, if my mass number goes up only by 1, you can't change number of neutrons, so your number of protons, so your neutrons must go up. You get 69. We go up 1 more, gives me 70. Now be careful. What happens? We go up 4. So we go up 4 neutrons. They'll do that sometimes. Questions. You get in the habit of just doing one more, and then, get you. Okay, so now we're going to move on. That's kind of our basic rehashing. We're going to talk about radioactivity. This is something I don't know if y'all covered a lot in high school chemistry. Probably not so much. Okay, so there are different kinds of radiation because there are different kinds of particles that are emitted from radioactive material. And I'm going to tell you that this table is super important and you should memorize it. I try to be upfront about the different things that you really have to know. This is one of them. So make yourself a little note that says, I'm gonna memorize this. So we have different kinds of radiation that are produced from nuclear reactions. These reactions are super fun and easy to balance as opposed to balancing regular equations. Super easy. All you have to be able to do is if I tell you it's alpha radiation, you have to be able to write the symbol. If you can do that, you're going to be perfectly fine. So really, out of this table, if you know this, you can figure out the rest. So these are the 2 super important columns. So let's try to use what we know. All right, what is the charge on a beta particle? If we look for a beta particle, if you know the abbreviation for it, can you tell me a charge? Absolutely. What's the charge? -1. So when we have a beta particle being emitted, what's happening? Careful. Okay. So when you have beta radiation, what's happening is that you emit an electron. You do emit an electron, but at the same time that you emit an electron, a neutron is becoming a proton. So if a neutron becomes a proton and you had an overall charge, right, it's going to change. And that's why you have that -1, right? You're emitting a electron, and then you have a neutron that's converted to a proton. Okay, how about an alpha particle? An alpha particle is just like a helium nucleus. A helium nucleus has 2 protons and it has 2 neutrons. What's my overall charge? +2. Okay, how about a positron? This should give you a hint on what the charge should be. And a positron is kind of like the opposite of an electron, right? So an electron has a -1, a positron has a +1. Okay. All right, let's see. What form of ionizing radiation is most similar to X-ray radiation, and how is it different? So the interesting thing about X-ray radiation is it's one of the only kinds of radiation, not one of, but in that form of radiation, no particles are emitted. So like in alpha radiation, you're emitting protons and neutrons. In X-ray radiation, you're not emitting particles, you're emitting waves of light. So what other form of radiation is like that? Gamma is most similar, but how's it different? It's the strength of them. Are you okay going to get an X-ray? Sure, absolutely, no big deal, right? I do not want to be bombarded by gamma radiation. I will not be okay, right? So how's it different? Gamma is stronger or more dangerous. So I told y'all in the video that I've worked with radiation in the past, right? So I did not work with gamma radiation. I did not work with the most dangerous form of radiation. But what I worked with, number one, I had a lab coat that was just for doing radioactive work. I didn't wear it for anything else. I would get my radiation, it was in this like double container, right? And I'd take it into a radiation room. There was one room where all the radiation stayed. And I would take it to a hood. So I had this big glass, it's not glass, it's really plexiglass, but that would come down between me and what I was working with. So I'd put it in the hood. And then before I would open it, there was another layer, another like shield inside the hood. So I had like 2 layers of shielding between me and the radiation, and then I could open it. And I never, ever, ever took radiation outside from behind that shielding. It's serious. You do not want it to build up inside of your body because it will damage your body. What's the most sensitive part of your cell? Any cell in your body. You mess it up. What's in the nucleus? DNA. So if you damage the nucleus, the DNA inside of the nucleus with radiation, your cell is kaput. That's it. Done. So safety was a huge thing. Like we had a Geiger counter, a little handheld Geiger counter, and when you were done, you had to take that Geiger counter and run it all over yourself, all over the floor, all over the counters, just to make sure that you weren't spreading radiation. And we would have safety officers who would come in and they would say, okay, show us how you handle the radiation. And so you'd have to show them everything. And I don't know why, but I always got volunteered to be the one who would do that. It was only, you only had to do one person from the lab, and they're all like, you do it. So I would do it. And I remember one time I got in trouble because I had my Geiger counter, I laid it all over myself. But one thing that you have to be very careful about is that you do the bottom of your shoes. And so I did the bottom of my shoe. I went over the front, and then I came back, and I went over the back. But I didn't overlap the Geiger counter, right? And they like dinged me because I only went up 2. It didn't overlap. I was like, golly, you guys. But safety first, right? It is very dangerous. So that's why if you work with radiation, you get a little badge, a little radiation badge, and it's either you wear it, like I wore it on my lab coat, or they have like a ring version. And it's associated with your social security number. So what if you go from working in a lab to being an X-ray technician? you want to know your total lifetime accumulation of radiation. So that is going to follow you. And so they keep it in a centralized database and that kind of thing. But it's really for your protection. It's a good thing. So, okay, that was a really long side note. But sometimes that's fun to go off on little tangents, right? Okay, so, oh, this is perfect. If high doses of radiation can be harmful, what's the rationale behind radiation therapy for people with cancer? Say it again. Okay, so cancer by definition is a cell with rapid replication. That's true. And we know that radiation kills cancer cells. Why? Did we quite connect the dots there? Close. Why is a cancer cell a bigger target? You're right. Why is a cancer cell a bigger target? No, not because they clump together.
Because they're rapidly, I think the right word to use.
They're rapidly dividing. What gets exposed every time a cell replicates? What has to unwind? DNA. So every time the DNA is exposed, it is susceptible to radiation. So is every single cell in your body susceptible to radiation? Absolutely. Cancer cells are more susceptible because their DNA is exposed more often. So cell with rapid replication, so DNA is exposed to the radiation more than like a normal cell. So tell me if you've known anybody who's had radiation therapy, how do they feel? They feel terrible. You're killing their cells. You are. You're just hoping that the cancer dies before they do. I mean, it's effective, but it's barbaric. I mean, you know, like I hope that in 100 years we look back and we go, wow, I can't believe we ever did that to people. But it's what we got, you know, and we're all working on different ways to treat cancer. But right now, that's effective, right? Now, tell me it's the same thing's true about chemotherapy. If you give somebody a drug, right, a toxic drug, that's what chemotherapy is. Cells are gonna take it up and they're gonna die. Why do we use it in cancer? The cancer cells are rapidly growing. So the faster they grow, the more nutrients they need. So they're going to take up more of that chemotherapeutic than your normal cells. So they're going to die first because they're taking up more of this toxin. And that's the goal. That's great. Tell me, what are specific symptoms of somebody who's undergoing chemo or radiation? Hair loss. What else? They're nauseous, they're sick all the time. Tell me about the cells in your hair. How quickly do they replicate? Very fast. Your stomach, you have stomach acid. You have acid in your stomach. Those cells have to replicate fast because they're in a pretty toxic environment to start with. So the reason that you are nauseous if you have chemo or radiation is because you're killing off those cells in your stomach that produce the mucus that lines your stomach that keeps you from feeling sick, right? Otherwise, you're feeling the effects of your stomach acid, and that's what makes you nauseous. So that's why patients who have radiation or chemo have those symptoms. So if we're going to use radiation and chemotherapy to treat patients, we need to be super careful that we are giving them only what they need, right? Either for detection or for treatment. And you don't give them too much because you could very, very easily hurt them, right? Okay, that was a fun side note too. All right. How many simultaneous chest x-rays would a person have to endure to have an exposure of 20,000 millirems, causing a temporary decrease in white blood cells? Based on this example, is one chest x-ray harmful? So let's use the information in the question above where it said you're getting about 5 millirems of radiation for an x-ray. Let's just use that, right? So we're going to say one x-ray is equal to 5 millirems. So how am I going to set that up? I would need to have X number of x-rays, right? And if I get, what did I say, 5 millirems per x-ray to get to 20,000 millirems, right? My x-rays cancel. So then 5 divided by 20,000 is what? You would need to have 4,000 x-rays. 4,000. Anybody planning on getting 4,000 x-rays? No. So do you need to feel like it's dangerous to go get an x-ray? No, you can go get an x-ray. It's okay, right? It's fine. Go get an x-ray. And so what we look at, if you remember from the lecture, I gave you a table and it kind of said, you know, depending on the dosage of millirems, what's going to happen to the body. And the first time that we see a physiological effect on the body is we see a decrease in white blood cell count, right? And this is why we worry about those patients who are undergoing chemotherapy and radiation. Because what happens when you drop your white blood cell count? You can't fight infection. So these people are sick, right? You're putting toxins inside of their body, and now they can't fight infection. They are a super susceptible group, right? So you have to be very, very careful to take very, very good care of them. All right. Oh, and my other thing is, okay, so if you're an x-ray technician, are you going to facilitate 4,000 x-rays? Yes, you are. So what do we do for the x-ray technicians that we don't do for patients? They can wear the lead vest. Sometimes they're like in a separate room, right? But they protect themselves from an accumulation of x-rays, which is really important. All right, let's see. I think I did like a couple in a row. I don't know why I did that, but okay. So we're doing good on time. All right. Nuclear equations and radioactive decay. Nuclear equations are so easy once you know those two columns from the table. If you know those two columns from the table, balancing these equations really is easy peasy lemon squeezy. It really is. And somebody told me that I did mess up on the video. When I was doing the video, I did A, B, C, and then I jumped down here and did this D. So I'm sorry. I don't want to watch it going on. So we'll come back up and grab this D when we finish A and C, A through C. Okay? So my bad. I just, you know, human. All right. So thorium-232 is going to undergo alpha decay. How would we write an equation for that? What's the abbreviation for thorium? Check my chat. So what is it? TH-232. Okay. So what happens? What's my atomic number for thorium? $90. Okay, now this is the only tricky part. It's undergoing alpha decay. You have to know what alpha decay is. What is alpha decay? That's our helium nucleus, right? So helium 4 and 2. If you remember that, you're going to be fine. But that part you have to remember. So I'm going to put that helium. I have a 4 here because I have 2 protons, 2 neutrons, and I have 2 protons. Now, this is so easy to balance. I want to know 2 plus some number is going to give me 90. Because just like a regular equation, you have to be balanced. We have to be balanced by number of protons, and we have to be balanced by mass number. So 2 plus what number is 90? 88. What element has 88 protons? If you look at 88, radium. Radium. Yeah. All right, so now we have to balance our mass numbers. So 4 plus what number is 232? So it is 228. How easy was that to balance? Like awesome, awesome. I've been through balancing equations. You can do this. I know you can do this.
I did one of these on the online homework.
Yeah.
And I entered it like that and it said incorrect. Yeah. Double checked it and all my numbers are right. But...
So you have to, there's a little tutorial that you can do, and you have to make sure it might be something to do with your super and subscripts. So you have to tell it that you're going to have an element that has both a superscript and a subscript.
It did that, like, for the beta decay, it was fine.
It was fine. Take a screenshot of it and email it to me, and I'll look at it and help you out. It's probably just an entering,
Right.
and they wanted a particular way, and I'll look at it and I'll probably be able to, hopefully I'll be able to find it. But send it to me. Take a screenshot and then just send it to me in an email, and I'll do it. And if that happens to anybody else, let me know, okay? Because it is kind of particular in how it accepts an answer. It is.
I was kind of scared to try something different.
Yeah, just take a screenshot, send it to me. Okay, so strontium 92. Strontium, what's our symbol? SR. So we know this is strontium 92, and how many protons are in strontium? 38. Okay, so now we're undergoing beta decay. Remind me, what is beta decay? This is the hard part. Remember, we release an electron.
And it converts a neutron.
Yeah, a neutron goes to a
It converts it from a,
neutron to a proton.
yeah, a neutron to a
Neutron to a proton. Okay, so now what we have to worry about is -1 plus something gives us 38. 39. So what element has 39 protons? What is it? Oh, yttrium. Why, yttrium. Yeah, they got crazy names, right? Okay, so then we have to worry about 0 plus something is 92. 92. Y'all got this. Okay. We got nitrogen 13 undergoing positron emission. So we have nitrogen, we know this is nitrogen 13. How many protons? Nitrogen is 7. So positron emission. Remember, positron is very similar to electron. So put your E, right? Because it's going to be really similar, except we're going to change the charge. So it's going to be a +1. Okay, now 7, okay, I'm sorry, 1 plus something is going to be 7. So 6 plus 1 is 7. So what has 6? Carbon, and then we say 0 plus something is going to be 13. 13. Nice and easy to balance. Then I got to come over here and squeeze in my D over here. So we're going to go up here and grab this one that I left off. So carbon 11 undergoing positron emission. So if I have carbon, it's carbon 11. Because it's carbon, we have to have 6 protons, and it's undergoing positron emission. So this is just like the one we just did. Put an E because it's just like an electron, except the charge is different. What do we make? We're going to make boron, and boron has how many protons? So 5 plus 1 is 6, and then my mass number is still going to be 11 because it was 0 here. Those are nice. Those are nice. Okay. All right, last one in this section. Write a balanced nuclear equation for the production of iodine 131 used in the treatment of some cancers from the beta decay of tellurium 131. When you see it as a word problem, the only extra twist that you have to worry about is what is decaying and what is being formed. So what's going to be on the reactant side and what's going to be on the product side. So tell me what's going to be on the reactant side. Tellurium right here. So this is going to be reactant. And what's going to be a product? Iodine 131 and what? And a beta particle, right? So this is going to be product. So you're actually given more information in this word problem than we were up above, right? Because up above we were given the reactant and we were given what kind of radiation was formed. Here, you're being told the reactant, the product element, and the radiation. So let's put it together. What do we have? Tellurium is TE, is that right? TE 131? Not 111. 131. How many protons? 52. All right, and now we're going to go beta decay. What is beta decay? It's our electron. So now, we're actually told that we're going to make iodine. I mean, this is easy. And how many protons are in iodine? 53. Does that make sense? Does 53 minus 1 equal to 52? Yes. Does 131 plus 0 equal 131? Yes, we are good. Yay. Well, yeah, because it's a math sentence, right? So everything on this side, if you add it together, must equal to this side. So that's really 52 is equal to -1 plus 53, or another way you could write that is 52 is equal to 53 minus 1. It's the same thing. Okay, so I know that that is as far as what I ask you to watch. But what I want to talk to you about for just a few minutes, because we have time, right? Yay, we're ahead of the game now, is radioactive decay. So when something decays, we write one formula for it. But do we take all our tellurium and turn it into iodine like that? Doesn't work that way. So the way it works is in what's called half-lives. And remember how I said we're going to give this to a patient, right? If I give them something radioactive, if I put something radioactive in their bodies, how long do I want it to be radioactive? Not long, not long, right? We use radioactive carbon dating, right? Carbon-14, we use that to date rocks. How old are rocks? Like really old. My mom's a geologist, and so her time scale is super skewed compared to all of the rest of us, right? She's like, oh, give or take 10,000 years. What? But so the time scale for some radioactive isotopes, it takes a long time for them to decay. And then there are some that we can put in our bodies, and 8 hours later, basically gone. So what's different between the radioactive isotopes that we use to date rocks and what we actually put in our bodies is what's called the half-life. So the time it takes for half of the material to decay. to become non-radioactive. So let's use this example to talk about it. Let's say I have a patient, right? And I want to give them a dose of radiation. So let's say I give them 50 milligrams of this Tellurium-131. Okay? And I'm going to tell you, and I don't know what it is, I don't remember what it is offhand, but I'm going to assume the half-life, so the half-life is equal to 8 hours. No, I want to do, let's do it easier than that. Let's do 1 hour. 1 hour. I want to know 8 hours later how much of this radioactive thing is still inside of my patient, right? So let's do that. What happens in 1 half-life? 1 hour is equal to 1 half-life. What happens? Half of it goes away. So tell me what's left. 25 milligrams. Okay, now what's going to happen? I'm going to go another half-life. So now I'm at 2 hours, or 2 half-lives. What do I have left? 12.5. Somebody get a calculator out, because I don't have this pre-done. All right. So what happens if I go 3 hours or 3 half-lives? And y'all can put it in the chat for me, so I can see. 6.25. All right. Now what if I go 4 hours? 3.125. Okay. I want to go 5 hours. 5 half-lives. 1.56. Okay, 6 hours. I'm going to run out of room. I'm gonna run out of room. Okay, what's after 6 hours? 0. Point what? 781. 781. Okay. 7 hours. 0.390. Close enough. All right. Then 8 hours. Here's what we wanted. 8 hours. After 8 hours, how much is left in my patient? 195 milligrams. 0.195 milligrams after 8 hours. So the body's going to not be quite so radioactive after just 8 hours, right? So you want to make sure when you're picking the right radioactive substance to either detect disease, because sometimes we use radioactive in that as well, and sometimes we use it to treat. So if you're going to use it to diagnose, you don't want to give them very much at all. The bare minimum, right? Because that's going to cause the least amount of damage. And then if you're using it to treat them, maybe you do want it to be quite a bit, but you want it to decay very, very rapidly so that it clears from the body. And the body's going to have additional ways to get it out of the system. Like you're going to urinate some of it out, right? So when you talk about decay in the natural world, in geology terms, right, there's a set half-life for that. But when we talk about inside of the body, there's the half-life that we just talked about, and then there's also the human body process that gets rid of it from the body as well. So maybe when you're urinating it, now the liquid in your toilet is a little bit radioactive. But so you have kind of a combination of ways that the body's getting rid of or going through the half-life, right? Okay, so that was my little spiel about the half-lives, and I'm going to call it there. So I feel like we're doing pretty good. So any questions? I think I hid my chat so that I could. What's that? For the next one, you have 6 and 7, I do believe. So if you go here to Moodle, that's a good question. So you want to come down here to pre-recorded lecture schedule and homework calendar. So for next time, see if I can minimize this. So today you had to watch 4 and 5. So for Monday, you're watching 6 and 7. Then your homework is going to be due on Wednesday at 9 p.m. But please don't ask me for help on Wednesday at 8 p.m. All right? Come get some help early if you need help. Y'all have a great afternoon. Happy Friday Eve. Okay, anybody on the chat need anything? Y'all okay? Oh, looks like I'm typing. So the difference between the two positron is a particle that's very, very similar to an electron, except it carries a positive charge instead of a negative charge. So whenever we write it, beta is the emission of electrons, we put an E. And then positron, just like an electron, we put an E, but the difference is this one's negative. Oh, and in this one, an electron is released, and a proton gets converted into, a neutron gets converted into a proton. No, but what are you emitting? Your new substance now will have a different number of protons, yes, but the substance that you emit, the charge on the substance you emit is an electron, so it's negative. It's a what? Correct. Correct. So whatever, this column is whatever's being released. A positive. Well, no, so it does exactly the same thing as a beta particle. So you have that same conversion, but what you're releasing, the actual radiation that you're releasing is positive. Whereas this one, the radiation you're releasing is negative. Oh, good. Then you're good. No. Does it? I can look, send me an email that says, would you check my ID and see if it's right? And I can do that for you. Absolutely. Check out. I don't think I know about it. Okay, so yeah. Pull up Moodle. Go to Moodle. What do you have? Okay. So send me an email and ask me, and that way, like, I can pull it up on my system, and I'll check. You can go to iCloud. You go to iCloud.com, and you can check that out. You can see, like, how many times you check in, how many points you have. Well, I use the actual one. But still, even if you use the actual, put it up on your phone. Go to iCloud.com. Okay, go to, I think it's the gears, if I remember correctly for y'all. No, that's not. First, where are your, let's go to the hamburger. So it should be, like, it was different on the phone. Do the little drop down on your person. Maybe that's where it is. There you go, preferences. It was different on. Okay. So you want forum preferences? Because that's what I'm posting to a forum. And you want don't automatically. Oh, it's so different in each one. But I would do yes to auto. When I post subscribing, oh no, that doesn't fix it. It's different on the phone. I fixed like 5 people on the phone. Select the preferences. Try notification preferences. I bet that's what it is. Okay, here we go. So feedback, keep on forum here. So see how you want turn into on. Yeah, the forum posts. I think just you don't need to digest. You just need to post. Okay. There you go. All right. So now I'm gonna remember for everything else. Absolutely. Absolutely. Is this the email? I got it with this. I don't know. Yeah, that'll work. Okay. So either you can get it individually, like every time I post, you'll get an email, or they'll give you a digest. That's the end of the day. So So if you want it right away, you can change it, or if there's a different.
Okay, that's good. That's good. Put the app on my phone so I always get the notification. I don't have to remember to go check it. Good. If too many other things going on, one less thing to actually do. When my kid starts school, it's gonna be crazy.
Yes. Okay, so no, not iCloud, Have I? Yeah. Mm-hmm. Absolutely, absolutely. And it depends, there are two different kinds of decay. The radioactive decay is independent of the initial concentration, which is why you can read it. Like, that's the whole thing behind it. Because your half-life for different chemical reactions, it's either the zero order, first order, or second order, right? And so all radioactive decay is the first order. Right. So it doesn't matter how much you start with, you can actually bake something. Everything else is dependent on an initial concentration. So the formula would work for only first order reactions.
Okay.
So yes and no.
It would just depend on what it is we're trying to look for.
Right.
Okay.
Right.
That's what I was curious about.
Yeah. That looks like the right color. Oh, yeah, it is. Yeah, you can track your. Okay, so three lists of determinants. So it looks like you checked in the first day and not the next one. I've been clicking it and it's like a little note on the check mark after I click it, so I thought that.
That's good. But then again, I'm new to the clicker, so I'm not
We're
exactly
gonna,
sure.
we're gonna figure it out. We are gonna figure it out.
So does that mean that all my answers that I've been putting?
Maybe not.
Okay.
If it's saying yes, I have some numbers that are not associated with people.
Okay.
So it might be that I have your number, but I don't have it associated with a name. And so then it just leaves your number and tells your name is absent. Okay, so wait, let me go to the right section. I might have to relog in. Okay, what's your name?
Madison Crosby.
Oh, Madison, I think you were the one who was in, like, you're in the wrong section. I think you were the one I was looking. Yes, you're in 5T, not 4T. So look on your clicker, go back one screen, go back again. See, you're enrolled in 4T, but you're in 5T.
Okay.
So you need to do the little plus sign. Nichols. I don't understand how you were in the right class on day one.
I'm not sure.
And the wrong class. So Chem 1. Back to space. And space 1. There you go. Okay, so C 5T. So join, confirm that course. Yes. Oh, that's ridiculous. Okay, and then swipe 4T off. Wait, leave that one. Oh, it's a dot one. See,
What should I do?
your instructor, join the class, because I didn't close it yet. You are checked in. Okay.
So I guess it didn't count in these classes.
Let me see. I don't know if there's a way for me to like convert from, okay, so let me close it so that it's not going on. Oh, I need to end this.